logic now. Okay, so we have been talking about propositional logic, okay, and we discussed truth tables last time of compound propositions. So now let us talk about logical equivalencies. We kind of referred to this idea before about logical equivalence. We discussed this last time, we mentioned it, but now let's look at it more formally, okay? Basically, two propositions are logically equivalent. That's the notion of equality in this context if they have the same truth table, okay? That's what the definition is. So before we get there, let's get some words out of the way. There are two special truth tables that we're interested in. One is the notion of a tautology, okay? Basically, a tautology, a proposition is called a tautology if it's always true, regardless of what the values of the individual variables are, okay? So that's what tautology is. If the proposition is true, regardless of the combination of the proposition and variables. And then on the other side of the spectrum, we have what we call a contradiction, which is when everything is false, okay? Your proposition is always false, regardless of the combination of values for the simple ones that make it. And then if you have a proposition that's neither a tautology nor a contradiction, meaning when you do the truth table, you get a mixture of truths and false, we call that a continuous, okay? So for example, contradiction, at the beginning of the semester, we did a little proof about why square root of 2 was not a rational number. We did that by contradiction, okay? So that's formally what a contradiction is, a proposition that's always false. Therefore, is negation. What's the negation of a contradiction? Would be a tautology, because when you negate, if a contradiction is something whose column is all false, right? What happens when you negate that column? Everything turns into true. That's what a proof by contradiction does. So you assume something, you get a contradiction, that means that what you assume was wrong is always false. So its opposite, its negation, is what must be true. Okay? That's the idea behind it. Yes?
Are you recording?
Yes, yes. Okay, so that's why we need this. Anyways, here are the two basic examples of what tautology and a contradiction are. So let me do a truth table for this. So for the first one, I'm gonna have P in here, and for the other one, we can also use P, so we can use the same table for both. Then I need negation P, and so now here we can have P or negation P, and then for the other one, we do P and negation P. So these are basic examples. So there is only one variable in place here, which is P. So how many rows do we need? It's only one variable, so we need two rows, right? True and false. That's it. So true, false. Let's fill in this little table. What's the next column?
False, true.
False, true. What's the next one?
True.
What operation are we doing? It's an OR operation, right? So remember, OR is true. If at least one of them is true, that's it. Okay? It's false only when both are false. That's not the case here. So this is true and true. And then what's the other operation? What's the last one? And. When is and true? When both sides are true. Now, that doesn't happen here, right? So that means we get false, false. So it's right here. It's what we call a tautology. Because, it's true regardless of the values of P and not P. Regardless of what P and not P are, this is always true. And the other one is what we mean by a contradiction. Okay? All right, so that's what tautologies or contradictions are. And then, as we mentioned before, logical equivalency, this is basically, our notion of equality when we talk about propositions. So we say that two propositions are logically equivalent if they have the same truth table, okay? Formally, to check, for example, if you think about, imagine that you want to run a little computer program that checks whether two given propositions are logically equivalent or not. If you follow that first sentence that I just told you, what you should do then is truth table for one proposition, truth table for another one, and then check the tables and see that the values are the same. This is a little bit expensive, okay? To do two tables, and then you need to run through the tables again and check to make sure the values are the same. Equivalently, and more practice, you can actually verify this in one table, which is basically this is what you form. You form the biconditional P and Q, okay? And if this is a tautology, then that means P and Q are logically equivalent. Because think about it. Tautology means that this is always true, right? What is the condition for a biconditional to be true? When is this true? We defined this last time. When is a biconditional true?
When P and Q have the same true or false value.
When they are the same, and that's exactly what being logically equivalent means, right? If P and Q have the same value, then they're logically equivalent. Well, if they have the same value, that means this will be true, right? So if this happens regardless of the combinations of all the components, that means that this is a tautology, okay? So logically equivalence means that when you do the biconditional, you get a tautology. So if you want to write a little program that checks where two propositions are equivalent, this is easier to do. Just form the biconditional and do one table. Make sure that you get a tautology, okay? But, in practice, if you have something short, sometimes it's easier to just do a table for this and then a table for the next one and look at it. But if you have something large and so on, might as well just do one table and form the bicondition. Okay? It's up to you. Questions about what it means to be logically equivalent? All right, and then we have two examples that we saw last time. Okay? Last time we saw that the conditional P implies Q is logically equivalent to another one, which is this one. What is this? Who tell me the name of this?
Conditional.
No, this one. What's the name of this? Corresponding to this condition.
Inverse.
No.
Negation.
No. Okay, you have to read the things that we have done. This is called a contrapositive. Okay? Remember, contrapositive is when you flip both and you negate them. Okay? And we argued last time that these two guys, they have the same truth table. We did it. So, we did it here. Should be down here at the end. So last time, we did the conditional, we did the contrapositive, and we showed that they have the same truth table. Okay? Same truth value. So that means if I add an extra column here with P implies Q, biconditional, if and only if the contrapositive, then I will get true, 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 because the values here, they all match. You understand this? So I will get my tautology. So because of this, we know that these two guys are logically equivalent. They mean the same thing. Okay? Now here. And then similarly, we saw last time as well that the biconditional is equivalent to two implications. The conditional and its converse. Okay? P implies Q and Q implies P. You're basically saying that both directions must hold at the same time. Okay? For the biconditional to make sense. And then we did here the truth table of biconditional, the truth table of P implies Q and Q implies P, and you can see they are both the same. Okay? So those are two examples that we have seen of logical equivalence. And that's why I don't justify it to you, because we did it last time. I'm just using those as an example. Okay? So this is from last time. You can see that. From last time. So it's good to remember this, that conditional is equivalent to its contrapositive, and when you have a biconditional, you can break it up like this. Okay? As an and statement. Just break it up into two conditionals. You okay with this? All right. Now, question: how do we negate an or and how do we negate an and statement? Okay. So the rule to negate or and and statements, there's a name for that. It's a very important one. It's called the Morgan's law. We're gonna prove this theorem. We're just gonna prove one. Number two is gonna be the same thing. So I'm just gonna prove one. Okay. So basically, this is the theorem that tells you how to negate an or and how to negate an and statement. And basically, the Morgan's law say, okay, if you have an or statement, the way that you negate it is, first of all, or turns into and. Okay, you flip it, turns into and you have to negate both parts. Okay, so this is not P and not Q. And then similarly, how do you negate an and statement? The and turns into or, and you have to negate both parts. So the negation of P and Q is negation P or negation Q. Okay, it's called the Morgan's law. And let's verify this. So I'm going to prove number one, and then number two, I'm going to leave it to you as a homework. How do we prove something like this? We're saying that these two things are logically equivalent, so all we have to verify is that they have the same truth table, right? or that the biconditional is tautology, however you want. That's all we need to do to verify this. So let's do it. Proof. Let's see, I'm gonna prove number one. So I wanna show that the negation of P or Q is logically equivalent to negation P and negation Q. So let's do this using the table. Okay, so we have PQ, those are my main variables. Now, let's see, I'm gonna do it with the biconditional, that way we practice more making a table and you see a tautology thing. But again, you could just do a column for to have this guy and then another column for the other one, for the other side, and then compare the columns, okay? We're human, so it's easy for us to quickly look at it and compare. And when it's a computer, that's expensive in general. Like if you have, I don't know, 1,024 rows, or 1,000,000 rows, then you have to go row by row and check and verify. So it's painful. For us, it's painful. The computer is not painful, but it takes time. Okay. But when it's small, you can just look at it. But anyway, for practice, I will use the bicondition. But let's see. Let me first work on the left. What else do I need to make that statement show up? We need P or Q, so we need another column. Are we ready then to have that statement? Yes, because when you have P or Q, all we need to do now is negate it. Remember, you need to practice how to build tables. Okay? In the exam, you have a paper, you have to make the table on your own. It's not going to be given to you. Just give you the proposition. All right, so this column will carry the value of this part. Now we need to have this part. What do I need for this part? I need not P, I need not Q. Do we have that? Do we have it in the table? No, so we need to put it, right? So I need a not P, I need a not Q. Are we ready then to have the right side? Yes, we just do the AND of those two columns, right? Now I have not P and not Q. If you don't feel like writing more, then you can stop here, and then what you need to do to finish the argument is when you fill the table, you need to compare these two columns and make sure that they match. Okay? I'm gonna do an extra column because I want to do the bicondition approach. Okay? But it's not really necessary. So now I'm gonna form my biconditional, which is basically, is exactly what you need to do, in the sense that exactly you're going to look at these two columns and then see whether the values are the same or not to decide if it should be true or false, right? That's what you decide by condition. Okay, so how many rows? 4 rows. What are they? So for P, what are the values? True, true, false, false. And then for Q? True, false, true, false. Yes? And now once you have this prepared, this is the preparation of the table. Now we start filling in. Now the table guides you. You just do it one by one. Okay, column by column. What needs to be done. Let's see. P or Q. What should I write? True. 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 False. Everybody understand this? Remember, OR is false only when both components are false. If at least one of them is true, then that's it. The OR is true. Okay? Remember, last time we wrote down the basic truth table for these basic operations. You need to know those because then you use those to build up more complicated ones. Okay? All right. Next column. What should we do? Let's number the columns so we can speak about them in numbers. That's 1, 2, column 3, 4, 5, 6, 7, and well, this is column 8. All right. So how do we compute column 4? What do I need to do? The opposite of what? Of column 3. So this is the negation of P or Q. So that means that's exactly column 3. So look at column 3 and negate it. Yes? So what do we write? False, false, false. True. We okay with this? All right. How do we do column 5? Negate column 1 because it's negation P. Yes? So that will be false, false, true, true. Column 6? Negate column 2. So that's false, true, false, true. Okay? Column 7? So do the conjunction or the and. Remember this and of 5 and 6, right? To 5 and 6. Okay. So what do I write? So false, 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 true. Yes. Now finally for number 8. By the way, at this point, if you didn't do this column, like I said, this is not necessary. If you don't do the last column, what you need to do now is compare and write me a sentence and say, look, these two guys are the same. Therefore, they are equivalent. Okay? But we're gonna do this. If everything is true, then we say tautology, we're done. Okay? So how do we do number 8? What column do we need to look? So we need to look column 4, column 7, right? That's what we have in each side. And then we compare. Let's see. If by condition, if F, if and only if F, what is it? Remember, by conditional is true when both sides are the same. And it's false if they are different. So false, false, so that's true. False, false, that's true. False, false, that's true. True, true, that's true. Yes? So now we see, okay, this is tautology. Now this thing is tautology. So we're done. This means that these two statements are indeed logically equivalent. Okay? Remember, we didn't know this. Okay? So we are trying to figure this out. So to figure this out, what you do is truth table and check. Now, similarly, you prove number 2. Okay? I'm going to leave that to you as homework. It's basically the same idea. Exactly the same. Okay? So you do that one yourself. But this is called De Morgan's law, and then this is going to form this together with, okay, something else, the 2 examples that I'm going to have below, and we're going to use that to be able to avoid truth table. Sometimes you can avoid truth table as you're about to see, because it could be painful, or at least time consuming to do a truth table, okay? So if you can avoid it, you should do so. Questions about De Morgan's law? All right, so in the homework, you will have examples of how to negate statements with sentences and so on, but this is basically the rule, okay? So just follow that rule. All right, so here are 2 important equivalencies that we're going to be using throughout. The first one is how to break up an implication. Okay, the basic operations are really negation and or. Let's say those are the basic ones. Implication and biconditionals, conditionals and biconditionals, they are good for us as humans, but they're not good for the computer. The computer can easily do a negation, they're just flipping a bit, and then that's it. It can easily do or, and it can easily do and. You do bitwise operations. For conditionals and biconditional, they cannot do that right away. But what we do is we turn them into an expression that contains only or and negation. And the point is that every expression in logic, in propositional logic, can be written with only using or, and negation. That's it. That means that you need to have a way to get rid of conditionals, and you need to have a way to get rid of biconditionals. I already gave you the recipe to get rid of a biconditional. How do you get rid of a biconditional? You turn it into 2 conditions. This right here tells you how to get rid of a biconditional. Whenever you see a double arrow, you can turn it into this expression. The conditional and is common. Now I'm going to show you how to get rid of the condition. So if you want to get rid of the biconditional in using just or, ands, and negation, this is the first step. The second step is breaking each of these parentheses down. Okay? And your classmate pointed that out last time. Here it is. When you have P implies Q, this is logically equivalent to negation P or Q. You're going to verify, then you just do a truth table and convince yourself that they're the same. And then there's no discussion. These 2 things, they mean the same. And let's just think about it intuitively. Remember, there is only one instance in which this implication is false. When is that? If the beginning is false, remember, automatically this is true. Remember, this is the weird truth table, right? So there's only one case in which this is false. Which one is it? When P is true and Q is false, right? Let's see. Let's go over here. Notice that if P is false, then not P is true, and then that will make the or automatically true without caring what Q is. Yes? So let's assume that P is true, so this part here is false, right? So if P is true, this part is false. Then when Q is true, it's fine. So the only case that this will be false is when Q is false. P true, Q false. That's exactly what happens here. P true, Q false. You understand this? So, just by saying that, you can see, by the way, you can do a truth table or you can write a paragraph saying what I just say in words. And that's a valid proof. Okay? You can just say, look, this guy is only false when P is true and Q is false. And then you need to argue in a couple of sentences that that's exactly what happens over here. And then you're good to go. But you just do the table and there's no need to write words, and because then if you write the wrong words, then you may think that you're conveying one idea and then you're not. But with the table, there is no discussion. But you can write paragraph. All right, so let me do this. So proof, I'm gonna prove both of these because these are very important. Number two, what's the importance of number two? It tells you how to negate a condition. Above, we saw how to negate or and. Now, if you want to negate an implication, this is how you do it. You negate it by saying P and not Q. For example, if I win the lottery, then I'm rich. What would be the negation of that statement? Using this rule is I win the lottery and I am not rich. You understand? That's what this is telling you, how to negate a sentence like that. If I win the lottery, then I'm rich. That's P implies Q. The negation will be I win the lottery and I am not rich. Okay? But let's convince ourselves that indeed those two things, they mean the same. Okay? The negation of the implication and that unstable. But let's do first number one. Okay, so number one, we're going to do it as usual. I'm going to use truth table. It's easier. So use truth table. So I have P. This time I'm not going to use the biconditional. We're just going to compare. So I just see the two ways that it can be done. Okay? Before I did it using the biconditional, and now I'm going to do it without the last column. PQ. So I have everything I need for P implies Q. So we can do that. Let me use colors. And now I'm going to work with the right side. So what do I need for the right side? Do I need something? We need negation P, right? It's needed. Do we have everything we need, all the ingredients to make up the right side? Yes, we have negation P and we have Q. So now we can do negation P or Q. That's the mindset that you need to have when you're building the table. What do I need? Look at your table, okay? You start putting columns. Do I have what I need to get this expression? If you don't, you start adding until you have what you need, okay? That's what you should be thinking about. Okay, how many rows? 4 rows. So true, true, false, false, and then true, false, true, false. Make sure that you follow this convention, okay? Make sure that you follow this convention. First of all, it guarantees that you're not missing any case, and second, it gives uniformity in what we're doing, okay? The columns, you may do in whatever order you want, but the rows, they have to be in this specific order. Okay, let's fill in the implication. What do I write?
True.
True.
False.
False.
True.
True. And true. Okay? All right. So, negation P, what is this?
False.
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 True.
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 And true. Yes? And now, let's do the last one. What do I write?
True.
So, true. Good. Then? False. Remember, here you have to look at column 2 and column 4. Okay? And do the OR. So there's a true here, so that's true. These two guys are false, so this is false. So now this will be true, and the last one is true as well. Remember, we're doing OR. Now, you take a look at it and you say, look, these guys are the same. Right? So that's all you need, right? Same truth table. Imagine that if I had done the last column with the biconditional, what will happen in that column? What is it that we're going to get?
All true.
All truths, because these two guys are the same. When you do biconditional, you get all truths, so it's a top. Right? So it doesn't matter what you do or not. But again, if you are writing a little program, that's more efficient because you just do one table. You don't have to do this comparison. Okay. I mean, the comparison is implicit when but maybe you already have a function already programmed that's biconditional, so then it's more automatic. Okay, so they are the same, therefore, indeed, let me say, so it follows then that P implies Q, is logically equivalent to negation P or Q. All right. So this is what tells you how to break up an implication. Now I'm going to prove number 2, but I'm not going to do it with a table. I'm going to show you how we can now use the basic stuff that we know to verify all the logical equivalences without having to rely on the table. That's important because in this case, not that bad. It's only 2 variables, but if you have something that involves 3 or more variables, doing a table will require, if it's 3 variables, how many rows? 8. If it's 4 variables, how many rows? 16. You really want to do a 16-row table. You know, if you have to, then you have to, but if you can avoid it, you should. Okay? So then there will be many places for mistakes, many rooms for mistakes, so you have to be careful. So as number 1, let's prove number 2. This time I'm gonna do it with no table. Okay? Let me show you. All right. Basically, the idea is I want to show that the left is logically equivalent to the right. Now you should understand that there is a transitivity property here. For example, if P is equivalent to Q and Q is equivalent to R, what can we say about P and R? What do you think we can say about P and R? They're equivalent. I mean, P equivalent to Q means that the table of P and Q are the same, right? Like the values of P and Q are the same. Now, Q equivalent to R means the value of Q are the same as the values of R. Well, then what about P and R? Well, they're the same, like transitivity, right? So that means that I can actually start with one side and start forming a chain of equivalencies. So I can say, okay, this guy is equivalent to something. That something is equivalent to something else until eventually I get down to the right side and then you're done. That's how you solve equations, right? You start with some equation, you change it into another equation, until eventually you get to x equal whatever, right? What you're doing is you're writing a sequence of equivalent equations, all having the same solution. Until you get to a simple one that tells you that x equals 5. What's the solution? X equals 5. There's nothing more to do, right? So we're going to follow the same idea. So we're going to be solving a little equation here. All right, so I'm going to start with the left side, just because, you know, we can use what we just learned. And then my goal is I'm going to be writing, you know, a sequence of equivalencies. And hopefully, at the end, I will end up with this. This is what I want. Okay, if we can do this, then we're done. Okay, so let's see. The first thing that we can do is, first of all, we have here the negation of P implies Q. So I don't know how to negate this that we were trying to actually prove, but I know how to negate or and statements, right? It's the Morgan's law, right? So that means if instead of this I had an or and I could then do something else. So question, can we write this as either or and? Yes, we can. That's exactly what we just did. This tells you that when you have P implies Q, you can write it as not P or Q. Yes? These two things are the same. So that's what I'm going to do. So this is equivalent to the negation of not P or Q. And the justification here is from exercise 1 above. Yes, all I did was replace this guy with this. They are the same, so I can replace it.
Can you also write it as not P and not Q?
Where did you get that from?
Notes. I don't know, maybe I wrote it down.
Not P and Q.
Never mind. Different.
Okay.
Never mind.
Okay.
So
This is equivalent to this. Everybody agree? Now, why is this helpful? Well, because now this is an or statement, and I have the negation of that. We have the Morgan's law, so we can do it. So what does the Morgan's law say? How do we negate an or statement? It turns into an and then what do you need to do? Negate each part. This triggers the negation, right? So this would be the negation of P and negation of Q. What do we use for this? The Morgan's law. So we'll say here the Morgan's. You know, you should justify your steps just so that we know what we're talking about. Okay, so this is equivalent to this is equivalent to this, so we're good. Now, even though we have not said, what do you think the negation of P should be equivalent what? What is this? Negation of the negation? It's just P, right? Basically, you're saying flip P and then flip it again, right? So you're gonna return to the original value.
Negative times negative.
Exactly, negative. The negative is positive, but this is the logic version of that, right? So negation of p, that's just p, and then the other part just stays the same. And here we can just say since the negation of the negation is just itself, okay? And we're done because we started with this and we ended with this, which is what our right hand side. So no need to do a table. We use what we already know to just a sequence of equivalence. Did you understand this? Okay. I mean, if I don't say anything, you're free to do whatever you want. You can either use a table or do this. But if I say verify this logical equivalence or prove that these two things are equivalent without using a table, if I say that in the problem, it means that you need to do something like this. Okay? If I don't say anything, it's up to you. Now, if you see 4 or 5 variables, you probably shouldn't do a table. Also, remember you have only 50 minutes for the exam. You want to really use 30 minutes of your time doing a 32-row table? Probably not. Okay? I'm not saying that that may happen, but if it happens, then that means table is probably not the way to go. Okay? All right. Are you okay with this? So, moral of these 2 important examples, it tells you how to break an implication into an OR with a negation and how to negate an implication. Moreover, if you combine this with the examples above, now that means that you can take any logical expression and write it only with OR and negation. Because by conditional, you can break it into a couple of conditionals, and then each conditional, you can break it like this. Okay? So technically, if you know OR, negation, and you're good to go. That's basically. But you know, in practice, as humans, we don't do that. Like, we have the table for conditional, so we use it. But okay, so now what I'm gonna do is I'm gonna give you tools so that you can do number 2, you know, stuff like number 2. Because right now we use what do we use? We have the organs, yes, and then we use this statement that you can break conditional as not P or Q. But there are other tools that you can use. Okay, so I'm gonna basically give you the rules of these operations. Okay, because everything is based on negation and or. These basic equivalences are just with those. Okay. All right. So these are the points of theorems. They have names, but I'm not gonna require you to know the names. Okay. I don't even remember the names. I just remember them. I see this and know what it is, but you know I don't remember that this is called domination law. But just for reference, it's there. Okay. So if you want to learn them, perfect. If not, as long as you know the statement, that's all it is. So they are written here. Let's just go through them to make sure that we understand. Okay. So these are basic logical equivalences. Okay. So let's go through it. For example, the capital T here stands for a proposition that's always true. So think of it as being a tautology. Okay, something that's always true regardless. And capital F here will stand for a contradiction, something that's always false, a proposition that is always false. Okay, so just think about it that way. So now P is any proposition. So let's think about it. If you have P and something that's always true, what do you think is the truth value of this expression? What would this depend on? It depends on P, right? If P is true, this will be true. If P is false, this will be false. Right? So this is equivalent to P. Does that make sense? This is like saying 2 times 1. That's just 2. Right? The 1 is not doing anything. So basically, this is telling you that a tautology is neutral with respect to the conjunction. If you do something and a tautology, that's just this something that you have in here. Does that make sense? That's like multiplying by 1 or adding by 0. Right? Tautology is neutral with respect to this operation. Okay? Now, if instead of and you have an or, the one that is neutral is a contradiction. Because if it's an or statement and you have here something that's always false, the truth value of this or statement depends entirely on this guy. If this guy is true, the whole thing will be true. If this guy is false, the whole thing is false. Yes? So P or false is just P. Does that make sense? So these are called the identity laws. Okay. So similarly, we have the domination law. This is like, you know, like 2 times 0. What is it? 0, right? Like 0 times whatever is just 0. Well, That happens with or and true and a tautology. So you have an or statement, and then you have here something that's automatically true. Do you really care what P is? No, this is true automatically. So it kills the P. I mean, I don't care. This is just true. Yes, that's why it's called domination though. And then similarly, when you have and, false, a contradiction is what dominates now. If you have an and statement and you already know that one piece is false, there is no need to look at the other part. You already know the outcome is false anyways. Does that make sense? Okay. So again, if you want to prove these little theorems or little propositions, just do the truth table and then convince yourself that they all have the same truth table. Okay. Remember, this F stands for something that's always false, and this T stands for something that's always true. Okay. Then the idempotent law. You know, if you do P or P, this is just P. You know, if P is true, this is true. If P is false, then this is false, right? So P or P, that's just P. And same thing with P and P. If you do P and P, that's just P, right? If P is true, that's true. If P is false, this is false. You okay with this? All right. We already encountered this one. Negation of the negation. That's just P itself, right? Now we have the commutativity law between or and with or and and. It's basically 2 plus 3 is the same thing as 3 plus 2, right? The order doesn't matter. Where you can do the same thing with or and and. If you do P or Q, that's the same thing as saying Q or P. So you're free to flip. Remember, implication, this is not the case. P implies Q is not the same as Q implies P. So not all operations are commutative, okay? For example, for numbers, division is not commutative. 10 divided by 2 is not the same thing as 2 divided by 10, right? Subtraction is not commutative. 3 minus 2 is not the same thing as 2 minus 3. Okay? However, addition, multiplication, they are. The order doesn't matter. So you need to know this basic rule when you're dealing with these operations. So commutativity, you're allowed to flip or, you're allowed to flip and, no problem. Okay? Associativity, this is how you place parentheses. For example, you know, if you have 2 plus 3 plus 5, you could do it like this, but you could also decide to do first 2 plus 3 and then do the 5, right? That's called associativity property. That you decide, it doesn't matter what order you decide to do the operation, at the end you will end up with the same result, okay? We can do the same thing. If you have 3 statements like this with or, it doesn't matter which one you do first. You can do the first 2 and then the result, do it with the last one, or do the last 2 and then the result, do it with the first one. Notice that the operation is the same, it's just or, okay? Same thing with and, okay? When there is a mixture, then you have to follow whatever the parentheses say. But this is called associativity property. Let me keep that one. Then similarly, we have the distributive laws. You know, like when you have, for example, 2 times x plus y, there's a distributive property that says that multiplication distributes over addition, right? So what is this? 2 times x plus 2 times y, right? Well, the same thing. Or distributes over and distributes over or. Okay? So here we say multiplication distributes over addition. Okay? That's the word that we use. Well, same thing here. So if this confuses you, just think of this as being times and this as being plus. Same thing here. Put a time here and a plus here. Okay? So P times Q, but then instead of time, do this operation. P or Q, parentheses, then and P or R. You understand this? And similarly here, P and Q, parentheses, or P and R. That's distributive property. Okay? Notice that this is 2 times x plus 2 times y. Okay? Exactly what you're used to. It's just that now is with the symbols. Just need to do it a couple of times until you get used to it. You okay with this? So I guess the hint is the operation that is in here is what goes in the middle. Okay? The operation that is inside here is what goes in the middle. All right. We already met this, the Morgan's law. Okay, that's part of our list of logical equivalences. And then these ones are a little bit less straightforward, so maybe we should say something about that. So these are called the absorption laws. So P or P and Q, this is basically just P. Okay, so about it, okay? Basically, all we need to do, basically this is telling you that when you have this statement, Q doesn't matter. P determines the value of the left side. That's what this is telling you. So let's verify this. You could just do a table and that's it, but we can just talk about it. So let's talk about it. Let's see. When P is true, what's the value of this statement? It's true because it's P or something. I don't care what the something is. P is true, that's it. This guy is true. Yes? Now, when P is false, what's the value of this? Let's see. This P here is false. Yes? And then this parenthesis, what happens? Because P is false, I don't care about Q. That makes this parenthesis false automatically. Exactly. You understand this? So you have false or false, so it's false. So again, in any instance, P is either true or false, and that determines exactly what happens here. Notice that we never really need to look at Q for anything. Do you understand this? So this guy is just P. And then similarly, if you have this, the and outside and the or inside, again, this is also P. So if P is true, this parenthesis is automatically true without looking at Q, and then true and true, that will be true. If P is false, then because it's an and, then there is a false outside that makes this false automatically without having to look at Q. All right. So again, that's just P. So these are the assumption laws, and then the negation laws. Let's see who can explain this to me. You understand this? Here you have P or not P. Regardless of what P is, I mean, if P is true, then not P is false, but then if P is false, not P is true. The point is that these two guys, they are opposites, so at any moment, one of them must be true. And because it's an or, then that's always true regardless. Yes? Actually, this is what we saw above, right? Our example of tautology. Oh, okay, and then I guess this one was our example of contradiction, right? A simple example of contradiction. So those are your basic logical equivalencies. You know, just write them down yourself later. Make sure that you get familiar with them because these are the basic rules that you're gonna use to be able to prove logical equivalencies without having to rely on tables. Okay? It's just like knowing how to multiply and add and so on. That's what we're doing here, but with logical expressions now. Okay? Yes.
Hopefully, it's a welcome to your attendance.
Attendance. Okay, good. Try these examples while I take attendance. Okay, let's try the first one. So number one. So we want to show that the left is equivalent to the right. Which one? You need to pick a side. Which one do you think we should begin with? The left, the most complicated one. You know, and then the idea is we want to simplify this until eventually we end up with that. Okay. So you start with the most complicated one, and typically the problem will guide you. It will just tell you what to do. Okay. One by one. Let's see. You have the negation of P or not P and Q. Okay, let's see. What do you think is the first step that we should do here? Distribute what? The negation. And what's that called? The Morgan's law, right? This is an or statement. So the first thing is to use the Morgan's law, right? So we can do that. In other words, let's get rid of these parentheses, right? How do you get rid of these parentheses? Distribute the negation. How do you distribute? That's what the Morgan's law says. So this would be negation P and the negation of this. Yes? So here you can just quickly, you know, somewhere write the Morgans. Okay? All right. So you should remember that name, the Morgans. Okay, the Morgans. Okay, what do you think should be the next thing to do here? There's another parenthesis, you know. You get rid of parentheses, right? So let's get rid of this parenthesis. How? Distribute the negation again. How do you distribute the negation? The Morgan's law. It's just the other version. Remember, there are two versions. Distributing over or, but then distributing over and. Okay? But the idea is exactly the same. So this stays like that, and then distribute, and you get the negation of P or negation of Q. Now it's important. Why am I putting these parentheses here? Because we have an and in front. Okay? So it's important because you have and this thing. So this thing is turning into this parenthesis. So that's why you have to turn, you know, this negation, this part right here is this or statement. And you need to do conjunction with not P, so I have to put in parentheses because I mean all of this with this guy. Okay? And do the and. So that parenthesis we use here? De Morgan's again. Yes? All right. Next, what else can we do? So it's a double negation. So let's get rid of that one. So it will be negation P and then we have P or negation Q. Yes? All right. So I guess here you can just say, well, I use the fact that if you don't remember the name, just write the rule. Okay? What we use? Those two things are the same. So we replace this with. What do you think we should do? Distribute. So to get rid of the parentheses, you distribute. Again, you see this, it's like seeing this. What do? You see that? You distribute, right? Well, that's actually what we do. We distribute. Okay? Just remember, instead of times and pluses, you're going to see ands and ors. But it's exactly the same idea. So let's distribute. Let's see, who can tell me what we get when we distribute? What do we get? Negation P and P, remember the parentheses, or negation P and negation Q. So here we use distributive property. Okay? All right. Now we need to evaluate the parentheses somehow. The good news is that notice that this parenthesis is already what we want, right? So somehow we need to make this thing go. Yes? Let's see if we can do it. Think about it. What is this? So what is this? This is always false. Yes? Because they have, if you want, this is your basic, this is this one right here. But you can just think about it. So this is always false. So this becomes false. Okay, this, I guess, yes. So we use the fact that not P and P, this is always false. And now what happens when you do false or something? What do you get? What do you mean true? You get that something, right? The value of this relies only on this one, right? That's called, what was that? Like the identity law, I think it was called. The identity property, that when you do false or something, is that something. If you do true and something, is that something, okay? So, this false here is not really doing anything for us. So this becomes just negation P and negation Q. The property that we use is that when you have false or, okay, P. Yeah, but if I put P, okay, understand that this P is not the same thing as a P in here. So I guess let me use something else. Let me put R. False or R is just R, right? Now R here stands for this parenthesis, okay? I don't want to put P because if I put P, you can get confused. That the P that I put here is not this P. It stands for this thing, right? Okay, and we're done. We started with the left, and then we arrived to the right. Playing with the properties. Did you understand this? And so, let's see, let me just quickly show you the last one. We need to show that this is a tautology. How do we do this? So you could do a truth table, okay? But again, the goal here is to stay away from truth table as possible. So what we need to do is play this game, and the hope is that eventually we end up with T only, like with something that's always true. That would tell us that this is a tautology, okay? So let me just quickly show you how it is. And like your classmate pointed out, the first thing that we need to do is, because the basic rules, notice I never tell you anything about implication, okay? So the first thing you need to do is break off any implication, any conditional or biconditional, break them off. And then we can use the basic rules. So that's the first thing that we're going to do. We break off the conditional. How? You negate the first part. Then you do or the second part, okay? Remember, it's negation P or Q. That's how you break off P implies Q. So you negate the first part or the second part. Okay, so I'm just gonna do the whole steps without writing the justification. Next, I'm gonna use De Morgan's law. So that's negation P or negation Q, or P or Q. Yes? Now, the good news is that notice that everything now is or. It's just like having a bunch of processes. You can pick and choose, and you can decide to combine whatever you want. You can use distributive together with commutativity. You can move things around. Like, this is what I mean. If you have 2 plus 3 plus 4 plus 5, I can write this as 2 plus 5 plus 3 plus 4, I guess the same thing, and so on, okay? I can move things around. So basically, I want to put the p's together and the q's together. That's what I want to do. I can do that by doing commutativity and associativity. So we can write this as not p, or not q or q. Yes? We can do that because everything is or. If there was an and in here mixed with or, we cannot play this game. But we can do it. All right. Now, what is this parenthesis? This is true, right? That's one of the basic rules. This is true. And what's the other parenthesis? It's true. So true or true?
Always true.
It's always true. So this tells me that this guy is always true. So it means it's not true. Okay? So again, so when you're doing the homework problems, try to do some using tables about logical equivalence. Try to do some without tables so you can practice with this. Okay?
Scroll down.
Okay. Questions? All right. So you now know everything to finish homework 1. Okay? So I'm gonna be putting the quiz. The quiz is gonna be due when the homework 1 is due. Then you will have the quiz. So make sure that you finish the homework first. Then you do the quiz. Remember, the quiz is just from the homework, 4 or 5 questions. Okay? And more than that. So if you understand the homework, you can do the quiz without any issues. Next time, I guess on Wednesday, we're gonna look at quantifiers. I'm gonna ask you to watch some videos so you start getting in the mood for that. Okay? Remember, no class on Monday. All right.